In the Ergo PAM4 RX video, we discussed why you need it, but the Ergo PAM4 still has lots of limitations. So, we need to swap the order now and tell you why the ADC DSP-Based PAM4 RX is still a must in some applications. For example, your marketing sales VP may ask you why you cannot sell your Ergo PAM4 RX to other potential customers. Think about the input sensitivity images for 5 seconds. Correct. The input sensitivity of the PAM4 RX is more critical than the NRZ RX. Further, the TX PAM4 output eye shows the eye shape is different in the 3 eyes because of the non-linearity. Also, the eye is tiny because of the 1/3 of the eye opening for the 4 levels and the larger noise from the more active devices with a greater complexity. Then, the worst case or the smallest eye opening between the 3 eyes will determine the bit area at the TX output. Second, after the channel, the eye is totally closed because of the signal integrity degradation, such as reflection, insertion loss, etc. Third, at the RX front end, the CTOE or the preamplified VGA may not recover the signal integrity degradation well enough and still have a few residual ISI. In addition, the front-end CTOE VGA may also degrade the signal linearity further and compress any eye among the 3 eyes. From this reference, you can visualize the 3 eyes were not quite open, surrounded with lots of little green dots, which is the noise. Even after just a 6 dB channel loss, the PAM4 eye would be completely closed. If we apply the 15 dB channel loss at the Ergo front end RX, the eye opening we could achieve under the limit bit area after the CTOE, not very low, is only 20 mV. Furthermore, if we apply the 21 dB channel loss at the Ergo RX, the eye opening degrades to 16 mV, which has a less margin to tolerate more channel loss or more RX internal noise. Again, if we look at the RX internal eye scan closely, not only the eye height is little at the 20 dB loss, but also the eye width is less than 0.2 UI. Therefore, any more sinusoidal jitter SJ at the RX input will fail the required bit area quickly. In other words, even assuming a perfect slicer at the perfect threshold voltage in vertical and the perfect timing in the middle of the eye in horizontal, the Ergo PAM4 RX still have very limited input sensitivity, since the 2-bit ADC was not quite enough to capture those signal distortion noise well enough from such complicated impairment sources. If the 2-bit ADC were not enough, what would you do? Bingo! Just add more bits resolution in the front-end ADC. Make sense? To balance the power, performance, and area, etc. trade-offs, people choose the ADC resolution range from 6 to 8 bits, which indicates a signal-to-noise ratio SNR of 38 to 50 dB ideally. If the 6-bit ADC can really convert and provides the front-end signaling information precisely in the digitized format, the DSP can improve the residual signaling imperfection by different algorithms flexibility. The DSP is to help further reduce the residual ISI, reflection, nonlinearity, surprise noise, and minimizing intrinsic thermal noise. Then the eyes can equivalently see a bigger PAM4 eye and achieve a higher input sensitivity robustly over PVT. What's the benefit of a better input sensitivity at the eyes? I believe you should know it and try to think about it on your own for 5 seconds. Great. As we discussed in the NRZ eyes, the best eyes is to tolerate as many input impairments as it can without any error, or the same idea should apply to the PAM4 eyes, even though it's more difficult. So the NRZ eyes for the PCIe 5 and under must tolerate the external RJ, HJ, DMSI, CMSI, and ISI, including reasonable reflection, etc. impairments. Even though the PAM4 eyes would not need to tolerate all the impairments, but it should still face the input RJ, HJ, and ISI. Therefore, a higher input sensitivity would certainly can tolerate a higher channel loss in ISI or bigger input jitter within the same target bit array. On the other hand, a high input sensitivity will achieve a low bit array with the same input external impairments coming from the link partner. So, apparently, the analog PAM4 eyes would have less sensitivity than the ADC DSP-based PAM4 eyes. From the equalization point of view, we need to address here. If we are able to convert the analog signals to the digital with a much less quantization noise error, we could then use the digital data to represent the analog data precisely. Then the DSP will apply those digital data along with the complicated adaptive equalization algorithms to reduce the ISI effectively and precisely in different environments. In addition, the DSP using these techniques can adaptively compensate for channel distortion and optimize the RX intrinsic performance, making the system more tolerable to changing channel conditions. If we decide to apply the DSP assistant approach to improve the RX sensitivity, what's the integration and scalability image will you have? Think about SOC or advanced process images for 5 seconds. Right, to keep improving the SOC PPA performance, we must apply the most advanced technology, which benefits the digital circuits a lot. On the other hand, the analog blocks don't benefit from the most advanced process well, and that's also the trend of minimizing the number of analog blocks if we choose the ADC DSP-based PAM4 ARCs. Again, the DSP not only has the highest speed with the scaling area and power faster than the analog circuits, but also the DSP provides flexible configurability, enabling the digital ARCs to adapt to different data rates, maturation formats, and the channel characteristics. Therefore, the ADC DSP ARCs allows easy integration into any SoC or even FPGA designs to adapt to various applications requirements easily. Besides mission mode, does the DSP ARCs provide flexibility in the test mode? Think about the DFC image at the ARC's internal nodes for 5 seconds. Right, all the available digital data for internal analog behaviors simplifies the debugging and testability of the RX, which can be more easily observed and analyzed. The ADC DSP RX improve system reliability, faster development, and better system integration in DFT or monitoring in some key performance in the RX. For example, first, the AFE equalization performance would determine the input sensitivity of the RX. The on-chip frequency response of the CTOE can be read out and processed would be very useful. Second, unfortunately, the AFE nonlinearity, including the ADC, would also degrade the RX input sensitivity. Even though the equation is perfect, we must observe the AFE linearity and even optimize its linearity during the link training or background calibration if needed. Lastly, to achieve a lower bit error rate, we need to monitor the thermal noise or the voltage distribution such that we could even optimize the biasing over PVT to reduce the noise besides just reporting the noise contribution during the testing. So far, we know the ADC DSP RX is more robust than the analog RX, but its power might be high because of the high capacity in nature. What can we do? Think about the PVT images for 5 seconds. Bingo! We know the digital power scales with the process node P, so the DSP must leverage advanced semiconductor fabrication processes, and the digital design techniques can result in significant power savings. In addition, the ADC, including the front-end input buffer, also reduce power owing to a more advanced processes. For the temperature, we could limit the range to boost the input sensitivity margin or reliability. But the end user may define the temperature specification. In order to sell more to our all customers, there's nothing we as a chip provider can do with the specification. But you can monitor the critical blocks by adding the on-chip temperature sensors to incorporate with the DSP to boost the performance is a trend. How about the supply voltage? Think about the CVF current image for 5 seconds. Yes, the CVF current scales with the process C and the voltage V together, and the power is proportional to the square of the voltage. Therefore, you can see few people have a single supply voltage in the PAM4 series. Instead, you could use 0.67 volt, 0.8 volt, 1.0 volt, 1.2 volt, 4 supply voltage for different needs. For example, for low speed but very complicated big digital block, 0.67 volt can still meet the digital timing with big power saving. For most high-speed digital blocks, the 0.8 volt should be high enough between the speed and power trade-off. For higher linearity requirement, 1.0 volt can help the analog blocks under less distortion. Lastly, the 1.2 volt is a must for producing a 1.2 volt peak-to-peak differential TX output swing, along with a good linearity. Here are a summarized image showing why we need the ADC DSP-based PAM4 receiver. The first simple image is the marketing sales image, that you need to sell as many applications as possible. But there are lots of different links, including different channel loss. To be clear, your PAM4 receiver must be error-free, no matter the insertion loss is 10 dB, 20 dB, 30 dB, or even up to 50 dB range, such that your sales VP will be very happy. Unfortunately, the Ergo PAM4X has limited input sensitivity because of the limited voltage resolution and signal processing. So, first, the ADC DSP PAM4X will provide a higher input sensitivity by ADC's higher resolution, greater than 6 bits, along with a DSP to reduce or mitigate the error impairments such as equalization enhancement, linearity improvement, noise reduction, sampling phase optimization through the power adaptive algorithms. Then, second, the ADC DSP PAM4X not only can tolerate more input DJ, SJ, RJ, noise, ISI, reflection, nonlinear input, etc. external impairments, but also provide a good integration with SoC, FPGA, and test scalability in the most advanced technology, which improves the PPA a lot. Third, the ADC DSP PAM4X would be easier in the debugging and testing owing to all the available X internal error behaviors through the DSP. Lastly, by using the most advanced process and on-die temperature monitors, scalable supply voltage for the needs, the ADC DSP PAM4X would achieve a less power than the Ergo PAM4X under the same channel loss. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting.